Hello again. So today we are doing Equilibria. Hooray! Let's just remind ourselves a little bit about equilibria and how we calculate it. You will remember that when we're trying to work out equilibrium concentrations, we need these things called ice tables. Ice tables give us an idea of how many moles are left at equilibrium. So let's say I start off with 1 mole of nitrogen and 1 mole of hydrogen, and I let those react. And then at equilibrium, I have 0.4 moles of ammonia. Sometimes people look at these numbers and say, hang on, haven't you got to have 3 moles of hydrogen? Well, I can have just about as any moles as I damn well want. Thank you very much. I'm going to have probably more nitrogen in the reaction vessel than hydrogen, because hydrogen's expensive. It's a resource that I'm going to have to make from fossil fuels, whereas nitrogen is freely available in the air. And the more nitrogen I have in my system, the more the equilibrium is shifted to the right. Okay, so I'd probably have quite a lot more nitrogen in the container than hydrogen. Okay, so yeah, let's just start off with 1 mole of each. Let's keep it simple. And then equilibrium, I've got 0.4 moles there. So what's happened? Well, the equilibrium amount of ammonia has obviously gone up by 0.4. When I'm doing the change line here, remember that the change line needs to be in the same ratio as the balancing numbers. So 1 to 3 to 2. So if that's gone up by 0.4, then this will have gone down by 0.2. There's in a 1 to 2 ratio. And then this will have gone down by 0.6. So that gives me my final values here. The equilibrium value of nitrogen is on 0.8 and the equilibrium value of hydrogen is on 0.4. And then we can write ourselves an equilibrium constant expression. Remember, it's the concentrations of products over reactants, and then it's raised to the power of their balancing numbers. So NH3 squared over N2 times the concentration of H2 cubed. And then, of course, I'd need a volume. Let's say my volume is 2 dm cubed. And we have to change moles into concentrations by dividing by volume. So we've got ammonia up here would be, ammonia's here, 0.4 over 2 squared, 0.8 over 2, 0.4 over 2, all cubed. And to save you a bit of time and number crunching, that's 12.5. Units, well, it would be units of concentration squared over units of concentration times units of concentration cubed. So that's squared on the top and to the 4th power on the bottom. They will cancel. So it would be 1 over units of concentration squared. So that's 1 over mole squared is mole minus 2. And dm, so it's 1 over dm to the minus 6 is dm 6. Phew, just about fitted it on there. Okay, that's all grand, but unfortunately not not really enough, because these are all concentration values, and it's unusual to think about the concentrations of things in the gas phase because we don't usually measure the concentration of gas phase substances. I mean, we can, but generally concentrations are for solutions. If we have gases, it's much more convenient to measure their pressure or more specifically, something called partial pressure. So the partial pressure of a gas is the pressure that gas would have if it was the only gas in the container. So let's say we've got two gases in a container. Okay, what we're going to do is imagine that gas is a combination of the two separate gases. So something like this. Okay, so my let's say my gas pressure here was 3 atmospheres. Then the pressure exerted by the blue gas would be 1 atmosphere, and the pressure exerted by the orange gas here would be 2 atmospheres, and the two together add up to the total pressure there. P tot. Okay. So how do we work out partial pressure? Well, partial pressure is worked out by the mole fraction of that gas. That gas makes up 1/3 of the number of moles, so therefore it makes up 1/3 of the pressure, and this gas makes up 2/3 of the moles, so therefore it makes up 2/3 of the pressure. So we're now in a position to calculate Kp. So Kp is the equilibrium constant for substances in the gas phase, and it's formulated in exactly the same way as Kc, except that now instead of having the concentration of ammonia squared, we'd have the partial pressure of ammonia squared. We no longer need brackets, just P subscript NH3 divided by the partial pressure of N2 and the partial pressure of H2 squared. Okay, so let's do this for this reaction here. So what we need to work out first is the total number of moles. Let's just put these numbers here, bring them over to this side. So we've got, these are moles here, 0.8, 0.4 and 0.4. Well, the total number of moles is just all of those added together, 1.6. Okay, so far so good. So the mole fraction of each will just be 0.8 over 1.6. Well, that's just a half. And for hydrogen, 0.4 over 1.6 is a quarter, and ammonia will be the same. So the mole fraction of nitrogen is a half, hydrogen's a quarter, and ammonia is a quarter. In other words, it makes up a quarter of the total number of moles in the container. Okay, so far so good. So now we can work out partial pressures. So partial pressure is the mole fraction of a gas times the total pressure. So for nitrogen here, the partial pressure will be the mole fraction, a half, times the total pressure. Well, we didn't decide a total pressure, did we? Let's say the total pressure is 100 kPa. Keep things at atmospheric pressure for the moment. And of course we do work in pascals, not atmospheres as I used down here. So the partial pressure of nitrogen will just be half of that, 50 kPa. Hydrogen will be a quarter of that, 25, and ammonia will be the same, kPa. So now we've got our partial pressures. Now we can plug those into our expression for Kp. So Kp is the pressure of ammonia squared, so 25 squared divided by nitrogen is 50 and hydrogen is 25, and then it's cubed. And again, to save you doing all the number crunching, that is 8 times 10 to the minus 4. Units, well, units would be, so it would be kPa squared over kPa times kPa cubed, which is 1 over kPa squared. So that's kPa to the minus 2. Now, some people say to me, well, hang on, we're working in kPa. Shouldn't we be working in SI units of pascals? That would be more appropriate. And I'm like, well, okay, you can if you want, but it's going to make your numbers bigger. So we'd have 25,000 squared on the top here times 50,000 times 25,000 cubed, which is just going to make the same number but with a different order of magnitude there. 8 times 10 to the minus 10, and now we're in pascals to the minus 2. We still get basically the same answer but with a different order of magnitude, unless it tells you specifically to convert your units. I would leave them in the same units that you're given. If you're given a question in kPa, I would leave it in kPa. Unless you're told specifically to convert those into pascals, it just gives you extra areas where you can go wrong. So the next video, all I'm going to do is literally just work through a question again, just work through this whole process, the ice table, mole fractions, partial pressures, and working out the value of Kp.